This video explains how to perform a link budget analysis in a wireless communication system. Link budget is a method of tabulating all losses and gains associated with the elements of transmitter system, receiver system, and also including the channel losses. This helps in computing the required transmit power, the minimum received power, the sensitivity of the receiver, etc. In link budget, all losses and gains are expressed in decibels. Now, let's see in detail the different power loss or gain associated with the elements of a wireless communication system using a simple illustration. The signal that is output from the transmit circuit results in the output transmit power. This is shown by a red line. The feeder circuit that is present in between that antenna and the transmit circuit causes a drop in signal power, which is denoted as feeder loss. The gain of the transmitting antenna will further increase the power level of the signal, and the signal is radiated from the transmitting antenna. This is shown by green line. Now, the effective isotropic radiated power is the output power from the transmit antenna minus the feeder loss plus the antenna gain. Similarly, at the receiving end, we have thermal noise floor. Actually, it is considered as the noise power in a bandwidth of B Hz. Noise power spectral density is minus 174 dBm per Hz and the bandwidth is expressed in dB Hz. The noise floor is added with the noise figure, that is the noise associated with the amplifiers, mixers, etc. present at the receiver circuit. We also need to account for the link margin, feeder loss, and finally the antenna gain, which will boost the signal power. So this is the minimum required power level. This is the minimum required power level at the receiver. However, we can also include a fading margin which accounts for channel effects, and therefore the minimum required power level will be higher. Now, the acceptable path loss is the difference between the EIRP and the minimum received power level or the minimum required power level. Let me explain an example from the book Wireless Communication by Andreas F. Molish. It is example 3.1 and the question is, consider the downlink of a GSM system. The carrier frequency is 950 MHz and the receiver sensitivity is minus 102 dBm. The output power of the transmit amplifier is 30 watts. The gain of and the antenna gain of the transmitting antenna is 10 dB and the aggregate attenuation of connectors, combiners, etc. is 5 dB. The fading margin is 12 dB and the breakpoint D break is at a distance of 100 meter. What distance can be covered? So let's tabulate all the parameters. So in transmitter end, the output power of the transmitter is 30 watts. In dBm, it is 45 dBm. The transmit antenna gain is 10 dB and all the losses is given as 5 dB. Similarly, at the receiver side, these are the parameters given. The receiver sensitivity as minus 102 dBm and the fading margin is 12 dB. So apart from that, the operating frequency is given as 950 MHz. That means that is the wavelength is lambda is C by frequency. The path loss at D break is D break, that is a distance of 100 meters. Before that, the significance of D break distance is actually D break is the distance from the transmitting end. From the transmitter end, the D break distance has 100 meters. So till D break distance, the path loss will be varying proportional to D power minus 2. So the path loss formula till d break distance is lambda by 4 pi d the whole square. So when we substitute the answers, we will get 6.32 into 10 to the power minus 8 watts or 72 dB. So the path loss is 72 dB. So beyond d break distance, the path loss will be proportional to d break power minus n, where the n represents the path loss exponent. So to understand all these clearly, let's see a small illustration. So the output transmit power is 30 watts, that is 45 dBm, and the loss is minus 5 dB, and the gain of the transmitting antenna is 10 dB. Therefore, the effective isotropic radiated power, which is equal to 45 dBm minus 5 dB plus 10 dB equal to 50 dBm. Actually, we can calculate dBm and dB together, because all these are logarithmic terms. So, which will result in 50 dBm. Similarly, at the receiving end, the receiver sensitivity is minus 102 dBm, and the received power level is 12 dB. So the minimum received power is 12 dB minus 102 dBm, which is equal to minus 90 dBm. Therefore, the admissible path loss is the effective isotropic radiated power, that is the admissible path loss between the transmitter and the receiver is the effective isotropic radiated power minus the minimum received power. So it is 50 dBm minus 90 dBm, it is 140 dB. The answer is 140 dB. And from the previous calculations, we found that the path loss till d break distance is minus 72 dB. The path loss till d break distance is minus 72 dB. So after d break, we have seen that it varies as d power minus n. So and again the path loss beyond d break, the formula is d by d break power n, where d represents the total distance between the transmitter and the receiver, where n is the path loss exponent. So if the total path loss is 140 dB and the path loss till d break is 72 dB, and we can calculate the remaining path loss as 68 dB. So when we equate this to this equation, so if n is 3.5, that means the path loss exponent, if you are assuming it as 3.5, then the coverage distance d can be computed as 8.8 kilometer. So from this link budget analysis, we could able to calculate the coverage, or we could able to find out the maximum coverage distance for this given scenario, and which is equal to 8.8 kilometer. I hope you understood the concept of link budget analysis in a wireless communication system. Thank you.